Okay, guys, welcome. Today we're going to talk about real population growth. Now, in our last video, we talked about the idea of doubling time and half-life. So we're going to be using some of those concepts again in this video. So if you haven't seen that video already, you might want to check that one out. But in this first example, we have that the average annual growth rate for the world population since 1650 has been about 0.7%. However, this annual rate has varied significantly. It peaked at about 2.1% during the 1960s and is currently, as of 2013, about 1.1%. Now we're going to find the approximate doubling time for each of these growth rates and use each doubling time to predict the world population in 2050 based on the 2013 population of 7.1 billion. So first we need to find all of these approximate doubling times. So we have 0.7%, we have 2.1%, and we also have 1.1%. Now remember that the approximate doubling time formula is T double is approximately equal to 70 over P, right, where P is the percentage. So for our first example, we would want to do 70 divided by 0.7. And if we do that, let's see, so 70 divided by 0.7 will give us 100. So T double is 100. If we have a 2.1%, then 70 divided by 2.1 would give us a 33.33. And for 1.1%, we have a 70 divided by 1.1, which would give us a 63.63. So those are the approximate doubling times for each of these different percentages. And you can see that for even slightly different percentages, these doubling times fluctuate pretty greatly, right? So now that we have the approximate doubling times, we can use each doubling time to predict the world population in 2050 and base that on the 2013 population of 7.1 billion. So of course, using the doubling time formula, y equals y0 times 2 to the little t over capital T here for T double. The only thing that's going to change in each of these each time is the T double, right? They're all going to be 7.1 billion for our initial rate, and then times 2 to the T. And of course, since we're going from 2013 to 2050, we need little t to be 37. And then we are going to vary this T double. So in the first one, we want 100. And then, of course, we'll want to do one where it's 7.1 times 2 to the 37 over 33.33. And then we'll use one that's 7.1 times 2 to the 37 over 63.63. Okay, so now we just have to calculate each of these. So for the first one, if I do 7.1 times 2 to the parentheses 37 divided by 100, we're going to get that this is equal to 9.18 roughly. Now, if we change our T double to 33.33, then we get that this is going to jump to 15.33 roughly. And then, of course, if we use 63.63, we're going to get that this is 10.62. Okay, so again, even with these small changes in percentages, you see that they have a pretty big effect on what the outcome of these calculations would be. Okay, Now, the next thing that we can talk about is the idea of a growth rate. Now, the world population growth rate was 37 births per 1,000 people, and the world death rate was 19 deaths per 1,000 people. Now, by 1975, the birth rate had fallen to 28 births per 100 people, but the death rate fell to 11 deaths per 1,000 people as well. Now, to find the overall growth rate, I need to take the birth rate minus the death rate. Right, so for example, in 1975, or sorry, 1950 is the first one. Right, I guess it's not marked here, but this should be 1950. So we have 37 births per 1,000 people, and we want to subtract 19 deaths per 1,000 people. And if we do that, it looks like we're going to get an 18 over 1,000. So that's our overall growth rate. So this is now births per 1,000 once we account for the deaths. And then in 1975, I would want to do 28 births per 1,000 people and then subtract 11 deaths per 1,000 people. So then we get 17 births per 1,000 people. Right? Now, of course, if this were to continue indefinitely, we would eventually run out of room, right? So that's what we're going to sort of focus on next. So as I was just mentioning, for any particular species in a given environment, we have something called the carrying capacity, which is the maximum sustainable population. So in other words, it's the largest population the environment can support for extended periods of time. Now, as the population approaches the carrying capacity, you get sort of a gradual leveling off that's happening. And this introduces the idea of logistic growth. Now, when the population is small relative to the carrying capacity, logistic growth is what describes this. And this is exponential with a fractional growth rate close to the base growth rate, R. Now, as the population approaches the carrying capacity, the logistic growth rate approaches 0. Right? Now, the fractional logistic growth rate at any particular time depends on the population at that time, and as well as the carrying capacity and the base growth rate R. And we can base that on this logistic growth rate formula. Now, to showcase what logistic growth looks like and how it's different from exponential growth, you can see that exponential growth is just going to continue in this fashion indefinitely, right, to the end of time. Now, logistic growth starts off exponential, but then as soon as we get to a certain point, we are starting to approach this carrying capacity, we start to level off, right? And that's because, again, the carrying capacity is the maximum population that can be sustained. So now in this next example, we have that the global population growth rate has been slowing since around 1960, when the growth rate was about 2.1% and the population was around 3 billion. Now, if we assume that these growth rate and population values represent one point in time on a logistic growth curve, and we assume a carrying capacity of 12 billion, we'll see, does this model successfully predict the 2013 growth rate of 1.1%? Given the 2013 population of 7.1 billion. So we want to use our logistic growth rate formula, right? So we'll call this logistic growth rate. And that's equal to R, which is our given growth rate, and then times 1 minus the population over the carrying capacity. Right? So that's sort of the idea. Now, what we're given so far is that we have our growth rate of 2.1% when the population was around 3 billion, right? And that was for the year 1960, of course. So what we can do, so this in 1960, we have 2.1% when the population was 3 billion. Right? Now, again, we don't know what our base growth rate is here, but we know that the logistic growth rate is 2.1% at some particular time, right? So this is equal to R, and then we have 1 minus the population, which is 3 billion, over the carrying capacity of 12 billion. So then this is going to give us that 2.1%, or we could even say that this is 0.021 is equal to R, our base growth rate, times 1 minus 1 over 4, right? If we reduce 3 over 12, that's 1 over 4. So we're going to get a 0.75, right? And then, of course, we could divide both sides by 0.75. And we would get that our base growth rate at this time would be that we get a 0.028, so 2.8% would be maybe our base growth rate. Now, does this model successfully predict the 2013 growth rate of 1.1% given the 2013 population of 7.1 billion? So now that we have this growth rate, and we're using our 0.028 as our base growth rate, does this give us 1.1% if we now plug all this stuff in, right? So now we're assuming that in 2013, the population is 7.1 billion over 12. And if we punch this into the calculator, will it give us 1.1%? So if I do 0.028 and multiply that by 1 minus 7.1 over 12, we're going to get that R, or not that R, we're going to get that our logistic growth rate is 0.0114, which is 1.14%. So in this case, it does give us a growth rate that's pretty close to what we would expect, right? We expected 1.1%, we got 1.14, which if we were to round would be exactly what we wanted. All right, so that concludes this video on real population growth. I hope you enjoyed, and I will see you next time.